Hi, this is Chapter 10 of Applied Statistical Analysis, Human Factors, and Psychology. Um, you can get all the materials at this website, which is also in the links, and you can download the materials we're going to use down in Chapter 10. The title of the chapter is Testing the Linear Model, and you can follow along with this R file, so download this to someplace convenient. The course book is located at this link, which you can get right here. I have downloaded the walkthrough right about here in a place in my documents, and I've now opened it up in RStudio. So in the previous chapter, we looked at how parameter estimates and beta weights are estimated in the linear model, but we didn't do any inferential tests, meaning we didn't do any tests of like null hypothesis tests, or actually even estimating the variability of our model. And that's what we're going to focus on today. So methods for testing the particular coefficients of the model. And you might kind of think, well, regression is, how is a regression similar to a t-test? So we already sort of know that a regression is similar to a correlation, but it's actually also similar, or else it can be framed to be similar to a t-test. For example, let's look at here. If we create a predictor that just has exactly two levels, and then we have an outcome that's related to the predictor plus some noise. So if I were to plot predictor outcome, you see that predictor level 0 has lower values than predictor level 1. I guess if I use aggregate, I can see the results. I can see the average for group 0 is negative 0.18 and the average for group 1 is 0.82. And so maybe we would find that these are statistically significantly different. And I can make a model predicting these two, just outcome tilde predictor, and I can plot that model here, and it looks like, okay, there's a slope for every unit increase in predictor, there's a about a 1 unit increase in the outcome. So although this is a correlation, this is similar to a correlation, are these two things correlated? It's also asking, is this different from this? And previously, if we wanted to test this, we wanted to do a null hypothesis inferential test, we would do something like this, t-test of outcome tilde predictor, and it would say, oh, this is significant, t is equal to 2.9, p is equal to 0.005, degrees of freedom is close to 38, and these are the means, negative 0.187 and plus 0.82. So now we've only really looked at just looking at the LM. What was this called? Model. Just looking at it and gives us these predictors. Now there's something funny here. Intercept is negative 0.187, and if we look at here, level 0 is negative 0.187. They're the same. And if we subtract these two, you'll find that it's equal to this, 1.01. It's almost exactly 1.01 unit difference, 1.01 difference. So these two numbers are embedded within the means of these two groups. So really it's saying at what level is this and what's the difference between this? So it's just coding these two values differently. And if you think about it, well, you can ask, what's this value? And then you can ask, how much does it increase here? Well, that amount of increase is exactly the same question if you want to see if it's significant as asking both about the slope or about a t-test between the two groups. And so the summary function for LM will give us not only the values but other statistics. If you look here, you can see that we have this estimate for the intercept is still negative 0.187, and there's a t-test associated with this, And then there's a predictor, 1.01, and there's a t-test equal to that. So now you need to pay attention to this line, 2.924, 0.0058, and 38 degrees of freedom. Now if we look up at the t-test, we did 2.924, 37.9, and 0.0058. These numbers are identical. And if I had, in fact, they might be a little different because this is using Welch's, but if it were a one sample t-test I did, they would be identical. So really, testing for the difference here in a t-test is formally the same. It's mathematically identical in this case to testing whether this slope is different from 0, because that's really what this is doing. For each of these predictors, now we have an intercept and a slope. It's asking, is this value likely to have appeared if there were no difference in the population that we sampled from? And here, a negative 0.18 is pretty likely to have occurred, but the predictor is very unlikely to have occurred, only 5.8 times in 1,000. And so we say, well, that's slope is unlikely to have occurred in studies this size that there were no difference, so I'm going to say it's significant and it's true. Okay, so there's a link here between t-tests and regression, and obviously there's a link between regression and correlation, but they're asking different things. It's not going to be true that if you do a correlation and a t-test, you're going to get the same insight in all cases. So what happens when we look at something like this, maybe not in categorical cases, but a continuous case, but the variability differs? So that's sort of the key here, because we know how to estimate the values, but we want to know how reliable this slope is, and we'd expect that we'd get a bunch of different slopes or have much poorer estimate of the slope if we had more noise. So here is, I'll just run these lines again, and here I'm going to create three linear models, 3 outcomes. In each case, I'm going to use a larger variance. So here's 5 units, standard deviations, here's 10, and here's 25. And let's see, I'm not going to be able to use plot 3D here, but I can use Plotly to visualize these. So here's one where I've got 2 predictors plus noise for an outcome, and you can see that, you know, they're not, it's at a slant so that both of these are in effect. And if you look at like down the line of this plane, the noise is pretty small. I can look at this one, and now the noise is a little bit larger. And I can look at this one, and now it's even larger. In each case, the plane that describes this relationship is roughly the same because it was created with the same model. Intercept of 10, a slope in the x direction of 3, and a slope in the y direction of 5. But the noise is different in each case. So if I were to try to estimate those parameter values, I can do that. And well, let's look at LM1, LM2, and LM3. You can see that you know, the true intercept was 10, and I get a little bit off here, a little bit off in the other direction here, and pretty far off here. This slope was 3, and I'm a little bit off here. I'm actually closer in this case, and I'm a little farther off here. And the last one is 5, and I'm really close here, a little bit farther off, and a lot farther off here. So if I did this a bunch of times, I'd expect that these would have a tighter distribution around the true values, and these would have a broader distribution around the true values because there's more and more noise. All right, so I can compute, though, the error. So these are going to be the best fitting lines. But there's more error in the Model 3 than Model 1. So I can take all the residuals of the model, like I can do LM1 resid, and these are points, how far were you off in each case. and I can square them and add them up, divide by n and take the square root to form a root mean squared error, which is an estimate of the standard deviation, residual standard deviation. So here it's 4.4, here it's 9.6, here it's 24.4, and so you can see that these values, the residual values, are actually pretty close to the noise I added. This is close to 5, this is close to 10, and this is close to 25. And so we fit the best line, and it's in each case a little bit under, but other than that, it tracks the noise I added to the data fairly well. Well, what if we were to do this multiple times? So here's a function that will do this repeatedly. And what I'm going to do is, on each time, create a data set like this. So rather than just having one, I'm going to create a bunch of data sets. And I'll do 1,000 different data sets, some with low noise, some with medium noise, and some with high noise. So I'm going to do, I'm going to use the same noise each time. I'm going to use this mid-level noise of 10. And that's what the standard deviation is I'm going to use. But I'm going to collect more and more data. So first I'm going to collect only 10 points, then I'm going to collect 100 points, and then 1,000 points. So if I run this, I'll go down here so you can see intermediate progress. It's going to go up to 1,000, and every 100 it's going to give this, and every loop it's going to put a little dot. So it goes pretty quickly, but I like to put this in so that you can see the progress. So what happens when you first look at the error term? So in each case, we fit a model and then computed the residual standard error. And I can make a histogram of these. So let's look at this. So this is just saying I'm fitting the model as best I can. I take every single residual, and I find my estimate of the error, and you can see that for just 10, the residual error was supposed to be about 10. That's what we put in here, and our best estimate is about 7. So just like before, we're a little underestimating what we found, and you can see that, well, good, it never goes below 0, but sometimes the model it comes up with is pretty good. Sometimes it's a lot worse. Now if we do more samples, we get a much tighter distribution, and if we do even more samples, a much tighter distribution. So this is identical to the notion of computing standard error when we're trying to estimate the mean of a normal distribution. The more points we have, the tighter the distribution we will have of that estimate. Each of these is going to also, we're going to want to compute each of our parameter estimates. And that's what's shown here in this really complicated figure. We'll see if it'll run. And I'm using layout to come up with a layout, a 4x4 layout, where there's like a little box up here and a little box on the side that I plot these things on that are smaller than these. So I'm using a pretty complicated layout function to do this. But now instead of the residual standard error, which is just the total error, the model will actually estimate each of these parameters, and we can see how close to truth the parameters are. And again, each of these this one was supposed to be 3 and the mean is 3, and this one's supposed to be 5 and the mean is really close to 5 in all these cases. But our variability when we only have 10 points is pretty large. And in fact, if we want to know if the intercept is different from 0, there's a significant proportion of observations that are less than 0, so we wouldn't necessarily even be convinced that it's greater than 0 if we observed any single one of these points. It would have to be pretty large for us to be convinced of that. In fact, it would have to be probably larger than the truth for us to be convinced that it's greater than 0. So that's something to think about. If you have a small, if you have a small pool sample and you find that it's significant, it's probably larger than it's likely to be larger than the truth. Otherwise, you wouldn't have found it to be significant. So this is the intercept, the slope with x and the slope with y. On average, if we do this a bunch of times, we get a unbiased answer. But on any particular one, we might get a slope from 0 to 6, or 2 to 8, or negative 10 to 30 in the intercept. But as we increase this, it also decreases, just like when we computed the mean and we want to look at the distribution of the mean, and that distribution of the mean gets very small as the number of samples gets larger. And so this scales just like the standard error does. This variability scales just like the standard error, along with the square root of n. This variability is going to be closely linked to the variability in the residual standard error. And in fact, this sort of gets divvied up between these pieces in order to figure out how much standard error belongs to each one. All right, so so how do we get those values out? Let's here's a data set that I created that we're going to be using. It's really the same thing as we saw before, I guess. And if we just look at LM1, we see the values. And I can get the residuals, lm1.resid, and I can apply this formula here. I'm going to, instead of taking the mean square residuals, we saw here that these looked like they were slightly biased, as if I just collected 10 samples, it would be on average less than 10. If it's 100, it ends up being close to 10, and if it's 1,000, it ends up being really close to 10. But part of this bias comes from having additional degrees of freedom that I'm estimating other parameters. And so just like we debiased standard error or standard deviation by dividing by n minus 1, we can similarly debias our estimate of the variance with this formula. So here's my estimate of the variance, the residual variance, 10.68 units, and that's for a standard deviation of 10. So if you look here and you look around on either side, maybe there's about a standard deviation of about 10 units on either side for this data. If I do a summary of LM1, summary does some additional processing that just looking at LM doesn't show you. It shows me statistical tests of each of the parameters, but importantly, it gives me a residual standard error. And you can see that the residual standard error of 10.68 on 46 degrees of freedom is exactly what I did here. I got 10.68, the same number. There's 50 points here, and it's n minus 4, 46. So that's what the residual standard error is. Like, you can see this number under summary, and it's really the sum squared deviations right here. Every deviation from the model, you square them, you add them all up, and then instead of finding the average, you divide by just a little bit of a correction factor, so n minus 4, and then you take the square root. So that's all this number is, and it represents an estimate of all the variability that we can't account for in the data. Now that has got to fit into our estimates of standard error here, because if we have more error here, we're going to have more error here. So now how do we get these values? Well, it actually basically comes from this value as well. So I'm going to create, before I showed you z predicted by x and y2, but now let's just look at z, x, and y. And I'm not going to do the corrected one because the correction is going to come in a little bit. And I'm going to do another model with just x. So I'm predicting z either by x or z by x and y. And so if I look at summary, let's do summary of LM2 and summary of LM3, I can see that when I have x and y, they're both significant. They both have values here. When I do just x, it's significant. You know, it turns out that because x and y are not completely orthogonal, my estimates change a little bit when I incorporate I. That means these are a little bit correlated in some way, so they counteract, and they're both highly significant. But this y value has an estimate, and it's got a standard error associated with it, and it's got a t-value associated with it. So this t-value comes from proportions of error that are in the larger model, or that are in the smaller model and that aren't in the larger model. So if we look at residual standard error here, it's 10.7. If we look at previous, it's 16.87. So in the smaller model, there's more error. We're accounting for less stuff. And so that additional error gets incorporated into this t-value. So the formula is here. I'm going to take the difference between the residuals and divide it by the residuals of the smaller model, because this is going to be larger, on the average amount of residuals in the smaller model divide with this correction. And if I look at t-value, it's 8.485, and you can look up here, 8.486. This is the same thing. So these things are computed by really comparing these residuals against one another, or it's equivalent of comparing the residual standard error, or a version of residuals for the larger model and the smaller model, scaled by the number of differences between these two, or the number of things that made into it. Okay, so this is the essence of testing the model. We can fit the model, but it's a separate process of testing. When we test it, we test it using summary. Summary gives us the inferential null hypothesis tests about the model, and it incorporates a couple different things. It incorporates, the model incorporates reporting the estimates of the intercept plus the slopes, and it does a t-test against each one of these. Now those t-tests can be interpreted in a couple different ways, and the first way is just as a t-test. So if you think about this, this has an estimate of 3.4, and you interpret each of these as a one sample t-test. So this is asking what is the chance. So if it says I've got this much standard error in my estimate, and it says, well, if the intercept really were 0, I can do, that's my null hypothesis, and I can say what's the chance of observing 10.96 if my estimate were really 0 and I collected this many data points and I had this much variability in my estimate, and this is the t-value, and that's the probability. So each one of these, this is asking, is my intercept different from 0? Normally your intercept being different or not from 0 isn't really interpretable. Sometimes it is, but only in very specific situations, and so oftentimes you don't even report whether the intercept is significant. You include it because it's just sort of you have to have it there. There has to be an intercept somewhere, but unless you have a very specific design, the whether the intercept is or is not different from 0 doesn't matter. Now there might be other levels that do matter, but in many cases the intercept doesn't. But in these cases, we also have an interpretation of a t-test in sort of a one sample test. Let's say the slope really was 0. What was the likelihood if the slope really was 0, and I have an estimated standard error of this, that I observed a value this large? And here it's very rare. It's got a t-value of this, it's got a p-value of this. Similarly, this one is very rare. It has a t and p-value of this. And so we can interpret this all as a set of t-tests. But there's another way. you can interpret it in terms of comparing models. So asking whether this is different from 0 is the same as asking whether this whole model is different from the model that doesn't include this. And this is maybe a little, these are really asking the same question, but they're really two sides of the same coin. And so that's why when we calculate this, we're not taking the deviation and subtracting the mean and stuff. It's kind of weird because if you expect the t-value to be a difference in means divided by your estimate of the standard error, and it doesn't look like that at all. I'm taking the difference between residuals and calculating it. So it's kind of strange that this even works. But really, it's asking an identical question in a different way. It's asking whether the model with intercept and x is worse or is the same as the intercept plus x plus y model. So the intercept plus x plus y model is, well, this residual 2 and 3 were x plus intercept, but the same thing holds. Okay, so this is maybe a more advanced way of thinking about it, and a lot of the model testing we'll do in the future in the ANOVA model and in the Bayes factor test, think about it this way rather than as a t-test. But they're both sort of true, so you can think about it however makes more sense to you. Okay, so that's a big thing that these provide. It provides estimates of your coefficients and whether those coefficients are likely to have occurred if the population really had a true value of 0. That's what that p-value is. But there's other stuff in here too. Let's talk about that. So we talked about the residual standard error. The degrees of freedom is going to be the number of observations, which is 50, minus the number of predictors, or the number of predictors plus 1, because I've got an intercept is 1, 2, 3. So 47 comes from 50 minus 3. Then it's got this multiple r squared. Well, what's that? In this case, it's 0.763, and I'm talking about LM2. In LM1, well, let's look at LM1. Summary LM1. This is the larger model, and I've got multiple r squared of 0.743, and that seems pretty good. How is that computed? Well, if I take the fitted values and compare it to the actual true values, which is in this case is z, that forms a correlation, and if I square it, that forms an r squared. And so it's 743. There's nothing tricky about this. I just take the predicted values and compare it with a correlation to the true values and square it. And because it's least squares, multiple r squared is good because it's also guaranteed to be sort of calibrated with the true values. So although correlation doesn't have to be calibrated, you could have a scalar difference and you'll get the same number. In this case, we will be on the same scale because we fit it so that it would be. So there's something about this that is a little unfair though, because I can add predictors and this can only go up. And so the multiple r squared is just, it doesn't care how many predictors I have. And so the adjusted r squared tries to correct for that by punishing you for having more predictors. And we can look at that here. Here's what happens when I try to predict a random value with a bunch of random values. So I'm going to create 10 different random predictors. And then we'll look at both r squared and adjusted r squared. So if I just give one predictor, q1, on z, which is completely unrelated to z, I can see, oh, r squared is 0.001, and adjusted r squared is actually negative here. The way it corrects it, it can create negative values out of positive values. If it's negative, you don't have to, it's just negative. It's just essentially 0. So there's nothing here, and there's going to be nothing in the adjusted r squared either. But now I can start increasing this. So if I make 2 predictors, well, it still is pretty bad. And my adjusted r squared is negative again. And if I have 3, well, it's still pretty bad. My r squared is 0.006. And here's 5 predictors. And with 5 predictors, I'm accounting for about 2% of the variance. and I could keep going, but here's what happens when I get 20 predictors and or 10 predictors. I account for about 20% of the variance, and you might be really happy with 20% of the variance accounted for, especially if it's a large social data set or large noisy data set. And you really may have 10 predictors. You may have a big data-ish data set where you have millions of people, you have ratings or information about 10 different aspects of them, and you might get a multiple r squared of 0.2 and say, oh, I can actually predict 20% of the variability. That's pretty good. But now if I do adjusted r squared, it adjusts it back down to essentially 0. Because remember, there really was no true relationship between z and all of these. So I'm only going to improve things if I give a bunch of these things, and I'm going to be able to get better. And if I give enough of them, they're only 50 points. If I give it 50 predictors, I will be able to predict every one of them exactly. And the adjusted r squared will punish you for that. It's I don't have the formula in here, but it's a pretty simple formula. R squared, we computed r squared by just doing the correlation and squaring it, but it's actually also identical to this formula, where you take this residual sum of squares divided by the sum of squares total and subtract from 1, because remember, we've always talked about how r squared is equivalent to the proportion of variance accounted for. Well, this is variance, and if we take this is the portion of variance I can't account for, the proportion of the residual divided by the total, I subtract from 1 and I get r squared. And adjusted r squared takes this and subtracts that from 1 and then punishes you for the number of predictors you have. And so it'll go down, and it ends up, because of this subtraction, being able to be less than 0 at times, even if your r, which doesn't really make sense. Your r squared can never be less than 0. You can never account for less than 0% of the variability, but with r squared, the adjustment is made such that it can go below 0. All right, so what else is in this LM? There's also, if we go back to summary of LM1, there's residual standard error, we know about that. There's multiple r squared and adjusted r squared, we know about that. There's this final line, and it's the F statistic. And sometimes people will look just at this, and this almost never tells you really what you want to know. Usually what you want to know involves these things. This is a very specific test. The F test is like a chi-squared test, and it's a proportion of variability divided by another proportion of variability. And usually the larger the value, the more likely it is to be significant, meaning the less likely it is to have arisen from the null hypothesis. So what you're saying is, I've got these 3 predictors here and 46 residual degrees of freedom, and if there were really no difference, I'd expect a certain distribution of on a scale comparing residual standard error. But the F statistic is always comparing 2 models. And with this F statistic, rather than comparing, like these are really comparing the model intercept plus x plus y plus y2 to intercept plus x plus y. This is comparing the whole model to the intercept only model. So this is just saying, does the whole thing altogether, is that better than nothing? You can't get there's no way you even have a model if you don't have the intercept. So your baseline model is an intercept only model, and this is just saying, does this whole thing altogether better than nothing, or better than the intercept only? And you can see that this is highly significant. And it's sort of misleading, because you might say, oh, I'm going to do a test of the whole model, but that doesn't say that everything in the model is useful. And in fact, we already know y2 is not useful. It just says, is the whole thing together useful compared to nothing? That's almost never what we want, and what we often will do then is do more specific f-tests. This is the f-test comparing the whole model to the intercept, but maybe we want to compare, well, the whole model to the model without a value. That's the f-test for the whole model to the model without y2 is actually going to be identical to this t-test. And so, but there's other types of comparisons you might want to do. You might want to say, well, here's the whole model, and then I've got one where I removed a bunch because they didn't seem to be weighing anything out, and I can compare the two and find that the F statistic shows that they're no different, meaning that the stuff you removed was not important. So that's all the pieces of that's all the pieces of the regression model, the standard regression model that you get with summary. Now, all of this testing is going to depend somewhat on you having a model with that doesn't violate the assumptions, like it's normally distributed and it's stationary and it's independent and things like that. And we're going to cover testing those in another chapter a little bit. So this is all working on the assumption that everything is normally distributed. All right, so the next thing I want to cover, is the Bayes factor test. So there are Bayes factors versions of this test, and they work more like this comparison of models test. So under the Bayes factor library, I'm going to reload this same data set I had before. And now the Bayes factor requires you to have a data frame. So I'm going to put all these within a data frame. And then there's a couple different Bayes factor models, and the simplest one is called LMBF. And if I just type, there is no summary function for this. It gives me a sort of overall Bayes factor test. This Bayes factor here is going to be the same, it's not the same number, but it's the same essential test as the F test of the overall model. So when I did this F test here, that's what the LMBF is going to compute, the equivalent of that. And you can see there's strong evidence for this model in comparison to the null model, which is the intercept only. You say against denominator intercept only. So even though we know y2 isn't important, this model is still better than the intercept only model. So you still have to think about, do I need all of these? Should I compare x and y2 versus x and y and see if that's any better? So on its own, the LMBF doesn't really help us much. But let's see. There's another function in the Bayes factor called regression BF. And this one works a little differently. And as these get larger, then you actually, what it does is it compares all possible pairings of models, every model with X and every model without X, and gives me the option of looking at them all. So if I now look at LM Bayes, it gives me 7 different models, and if you count them up, this accounts for all of the models with respect to the intercept only. So there's 8 models, there's the intercept only model, and then this tests every single one of these submodels against the intercept only model, x, y, y2, x plus y, x plus y2, y plus y2, x plus y plus y2. So they're all in there, from the most complicated one to the smallest one. If you look at this value, this should be the same as what we got in here. These are the interesting ones, and this is the equivalent of doing those t-tests. Now note that the Bayes regression doesn't give you estimates. If you want the estimates, you have to do the LM and get the estimates out of it. It's going to use exactly that model. But now we can say, well, is x different than the intercept? Or is really x plus the intercept different than the intercept only? Is y plus the intercept different? And here we see both x and y are better than the intercept because the values are very large. But now y2 is actually less than 1. It's fairly strong evidence against y2 being important. You know, it's 0.3, or it's less than 1 in 3, which you might say is strong evidence against y being important. But it's sort of near that cutoff. It's not certainly as big as this. So here again we have x plus y, and this is very large, which means x and y together are much, much better than the intercept alone. So you might say, well, both of these are good, and together they're good. Together, are they better than one of them? So what you can do is compare different rows of this with a ratio. And you do this, it kind of, it looks like you're just dividing these numbers, but when you divide the numbers, it prints this out, the comparison that you want. So here it says, I'm going to compare model 4 against model 2. So model 4 has x and y, and model 2 has just y. And so in the context of y, x is 231,000 times better. So than y alone. So that tells you why x is important even in the context of y. So even if they happen to be similar, x buys you more than y does alone. You can do a bunch of these types of comparisons to get at the different factors here, though. So if we look at LM Bayes 2, again, so I can take any one of these and form the ratio with any of the others to see if it matters. And so for example, 7 divided by 4, what about that one? LM Bayes 2, 7 divided by LM Bayes 2, 4. And here I can see it's very small, which means the evidence for this larger model with respect to the smaller model is actually really weak. We would prefer this model over this model. It's by a factor of 4. So this is maybe a kind of a more sensible way of doing this model comparison than you get with the null hypothesis test. But it's really quite similar to how we compare nested models within the normal regression or within the Bayes factor regression. All right, the last piece for this lecture is going to use some data from the Fairway library. So you download the Fairway library and you load it, and there's fruit fly data. So let's look at fruit fly. We have maybe about 124 observations of fruit flies. They've got a thorax size, they've got a longevity, how many days did they live, and they've got an activity. What is the activity level? Were they isolated? Were they with many others? Were they one other? They had low or high activity? So there's different behavioral conditions here. And so if we could ask, is thorax related to longevity? And that's easy to do. We do a linear model with longevity equal to thorax, and then because these are in a data frame, I can give it the data as a data frame name and then just refer to the column names or the variable names within that. So let's look at this. We can see that the intercept is less than 0. That doesn't really even mean anything because remember, we're asking, how does longevity relate to thorax size? Well, thorax size, whenever they measured it, could never be 0. So it's sort of immaterial that the intercept is negative 61. I could plot fruit fly, thorax, fruit fly, longevity, and let me try that again. I'll clear this. PCH 16 color equal gold. I'll zoom in, and you can see that this thorax size only ranges from 0.65 to 0.95, and so the fact that if we take this line and project it way over here to 0, that it's negative is sort of immaterial. But what's interesting is if there is a positive relationship here. And the test shows, yes, there's a positive relationship, 145. So how do I interpret that? For every 1 unit of thorax size, the longevity goes up by 145. That's kind of a strange thing too, because I don't even have 145 units. There's only like an 80 unit range in the longevity from the least to the oldest fruit fly. But I also have a very limited range in thorax. So, it's sort of for every, these are 1/20th of a unit. And so you could sort of scale that for every 1/20th of a unit, this goes up by about 9 units. So for every one of these, this goes up by about half of one of these. So that seems like it's reasonable. Well, I can make a prediction thorax based on longevity. But what about activity level? Activity level is categorical. So if I have a categorical variable, and you have to be careful that it's actually a factor. You have to make sure it's a factor here. But I can add it to my model. And if I do a summary, it gives me first an intercept, that same intercept. It gives me the slope with respect to thorax, so the same thing here. But now it gives me a single value with respect to 1, 2, 3, 4 levels of activity. If I look at levels of fruit fly activity, there's 5. Isolated, 1, low, many, high. So I only see 4 of these. And so when you give it a categorical predictor, what it does is it takes the first level of these and treats this as 0. So what your best get, and what it's doing is saying, essentially, I've got this main slope that has a negative 48 plus this slope. It's sort of a single line. That's going to be my best guess for isolated. And then every one of these activity levels is going to have a different, not a different slope, it's going to have a different intercept. So this slope is going to stay the same for everyone. And so if I want to put lines on here, it's going to be something like AB line, negative 48.7, 134. That's going to be for isolated. And now every other one of these is with respect to that model. And so if you want activity level 1, you add 2.6 to the intercept. So I'm going to just do 2.6. That's activity level 1, and it raises up a little bit. And activity level low is it's all going to change it with respect to the baseline model, which is the one not appearing here. So it's going to do it with respect to isolated. So here's another one. That's low. What about many? Many is, I'm going to add 4 units, 4.1. That's maybe the best one. And what about high? High is going to drop me down negative 20. So it turns out that you can see this here. The baseline, this slope is going to be with respect to all of them. I'm going to fit all of them with one slope. Even if there were different slopes within these, the model is not able to account for that. But so everyone gets the same slope, and what I'm doing is fitting different intercepts or different lines, a bunch of different models, one for each of these categorical levels. One of these was isolated. Activity 1 goes up a little bit. Activity low goes here. Activity many is the best one by just a nose, and activity high is the worst one by nose. So high level activity probably leads to significantly worse performance. And this is always, these tests are going to be always with respect to the 0 level. So they're going to be with respect to isolated, and so we can say that high activity is significantly worse than isolated. which was this guy. And in order to test whether it's different from another one, you'd have to do a different combination, but you can look at these and see which ones are significantly different. All right, so this way of framing the model in terms of intercept plus a difference from the intercept for each categorical level can be a little hard because you've got to do subtraction. So there's a little trick you can do, just like in the previous chapter where I showed how you can force the intercept to be 0. If you do that in this case, it's not necessarily intuitive what's going to happen, but it gets rid of the intercept, and now each categorical level, including isolated, gets its own intercept. And so these are just going to be the same values I calculated by hand before, but it makes it a little clearer. Now you can see I've got 5 different intercepts plus 1 slope describing this whole system. And so this might be easier to plot. Again, these coefficients are not, the fact that they're different from 0 is not really meaningful. What might be more interesting is whether these differ from one another. So that's how to add categorical predictors like this. You can also then think about, well, what if these slopes differ? How could I make it so these slopes differ? And so this fourth model is going to do the same thing, but let's look at it. It's going to say, this is a little different. It's going to say there's a common intercept and then a different slope for each one. So let's see what that looks like. I'll replot these. Plot, fruit, fly, Thor. Okay, so I'll replot this. And now we have different AB lines. So we have negative 53 as the intercept, and then I got 139.6 for one of them. Now this intercept's going to be the same here, but it's going to be 142, and it's going to be 131, and it's going to be 144, and the last one's going to be 114. So you can see that they all sort of will fan out from the same point. And we can actually see this if we say x lim is equal to 0, 1. Oh no, I have to specify the y limit as well. Negative 60, 100. So they all fan out from this point here, but they have different slopes. And so I would think that maybe this would be a reasonable model as well, that they sort of all start the same, but the effect of the activity is a growth rate rather than a absolute value. In this case, these slopes are really quite similar, so you could probably model it either way, and you might want to do something more complicated to figure this out, whether you really need both slope and intercept differences. It's a little further than we can go in this, but you can build that model by using a different type of interaction. So the colon interaction will just do the main interaction, so it does one intercept plus essentially a different slope for every value. If I do the times interaction like this, you can see that now this does an intercept plus a slope for thorax, so a main slope, plus a difference in the intercept for each group. This main slope is really the slope for isolated. So if you want just the isolated, it's going to be negative 50 with a slope of 136. And now every single activity, activity 1 is you're gonna adjust intercept plus and slope minus. And I don't want to draw all of these lines on here, but I'll say I'll pause it and draw those on in just a second. All right, so I took the different coefficients from this model and plotted them all on here, and you can see even when I have this interaction, we see a difference in intercepts and a difference in slopes, and the model doesn't look too different than what we did before. And so maybe there's a difference overall, but in this particular case, we maybe can't decide whether we want it to be modeled as a slope difference or an intercept difference. Okay, well that's the basic end of this chapter. We've got a few more topics about thinking about if you have a bunch of variables like this, how do we know we want to keep them? What are some of the ways we can do this? So we'll be dealing with that next in chapter 11, which is going to be about comparing models, variable selection, and making predictions. All right, thank you.